Good evening. How are we doing on OWL? We're figuring out how to get in, do the primers, kind of work with them. As you'll notice, every single class, I always start with a problem on the board, on the wall. So it's not, you can get started as soon as you join. You don't have to be here before class, but if you are, I want us to get in the right mindset to kind of think about how to move forward and what we're going to be doing today in class. So this is a follow-up on the POGL Activity 23. So if you still have that POGL Activity 23 that we didn't work on too much last class, please pull that out. We're just going to spend about 5 or 10 minutes on that. That entire packet and the POGL Activity 22 that I handed out are really good study tools. And some of it is reflective. A lot of Gen Chem 1 stuff, a little bit of Gen Chem 2. And really today is where we're going to start digging into Gen Chem 2 concepts. Maybe I'll come back to it. Someone remind me in like 10 minutes, maybe you want to get to the learning objectives when we have everyone here, to show a couple of the places to get resources in OWL that you might not have seen. Might not be intuitive. So I'll come back to that. So have we gotten everybody to click in? We have 20 responses on the iClicker so far. We're going to do a lot of iClicker questions today and most classes. I think we have more than 20 people. So make sure that you're logged into iClicker. You're submitting your responses. Because we have a ton of questions, you only have to answer 75% to get credit for the day. So we're going to move forward and hopefully get more responses in each corresponding question. So how do we answer this question? How do we figure out whether this is a polar or a non-polar molecule? And we're going to ask try to get everyone to speak at least once today. So pick your chance, and if you speak more than once, I'm going to try to see if someone else is willing to speak. Go ahead, Trace.
O2, if you it's just oxygen, so the electronegativity difference of oxygen is going to equal 0, so you know it's going to be non-polar.
Great, so we don't even need to draw a Lewis structure for this. So the normal steps are much more complicated, but we have two things that are the same. There's going to be some sort of bonding between them. We don't know if it's single or triple bond. Okay, we might remember that. And we can basically say that no difference in electronegativity in one bond means that this is going to be nonpolar. Okay, nice and straightforward. So let's go ahead and, looks kind of strange. We're going to do next compound. So I think this is, where is this in activity? This is in the exercises. This is exercise number 3. And actually the question I want you to do is I2. Sorry, it might look different in your phone. But so the next compound is I2. I'll give you about 30 seconds to click in whether that is a polar or non-polar molecule. Yeah, the image that it showed was one past this, so it sends a screenshot, and I sent the screenshot at the wrong time. So look at the screens, not your phone, for the compound, please.
Look at the screens.
The 8 screens around you. That wasn't meant to be smart, sorry. Yes, the large, obnoxiously abundant screens. All right, we got 24 responses. Can I have another volunteer? How do we decide whether this is polar or not? Yes?
It's 2 of the same element.
Same element, 2 of them. If we wanted to draw the Lewis structure, are you all comfortable drawing the Lewis structure for these? So we figure out how many valence electrons we have. Each iodine has 7 electrons. So we start out with 1 bond, we do the octet rule, and in this case, we're full. Is that the same with O2? Is it going to look the same?
No.
What's different about O2? So we have fewer electrons total. We have 6 valence electrons each. So we would do the same thing. We could then think about we only have 2 electrons past this point. So we can have octets for each element in the molecule by doing this. Okay, now let's go ahead and we had 28 to 1 for that. Non-polar. Alright, so now we're going to do the one that actually showed up on your screens a second ago. Carbon monoxide, think about the steps, write it down if you have. And if you have activity 23, by the way, if you notice, every single thing I hand out in class is hole punched. I really advise getting a little 3-ring binder and keeping the things, because I'm going to come back to the material we've used in previous class. So if you just bring that 3-ring binder with you, you get to add more and more to it, and it'll be your study packet kind of with everything together. Once you've submitted an answer, ask the person next to you if they agree and kind of see how they did it. How are you figuring it out? How are you answering this? Like, what's the process?
Using the chart of electricity, oxygen,
Okay. Okay. Two separate, not molecules. Atoms. Well, they're both. They are 2 atoms, and each one is a different element. Okay, a couple more seconds. Submit your response. Seven responses, and I'm trying to cheat and look on my phone where it shows a little app that's supposed to tell me what your responses are, but it isn't working. So if I'm on my phone when I'm walking around, I'm not just being rude. I'm actually trying to see what you guys are answering. Okay, so do we have agreement here? Can I have someone explain how you would answer this?
Oxygen's more electronegative than carbon.
Okay. So even if we don't know what the Lewis structure looks like, we can answer this pretty easily because we have a difference in electronegativity. So if we were to draw the dipoles that we talked about last class, what direction would the arrow point? To the right or to the left? Point towards the oxygen. And then if we wanted to do this right, do we know how to write a Lewis structure for this? Who wants to volunteer? Anyone? How many bonds do we have between them?
Well, the triple bond,
Okay. So you're saying triple bond and then?
lone pairs on each side.
So do we have the right number of valence electrons? We have 4 for carbon, 6 for oxygen. So that's a total of 10. We have 10 electrons drawn here. Does this look good though? Looks pretty ugly, right? Why? This is an ugly little structure. What's ugly about it? How many bonds does carbon always have? Always, always, always. Always has 4. Always. Unless you're in organic chemistry, and then it's not true anymore. So we oversimplify things a lot in general chemistry to get you to know the rules and the basic groundwork. And then we get to organic chemistry and we say, well, that doesn't apply in every case. And this is one of the cases where it doesn't apply. So in this case, what's the formal charge on the carbon? And if these terms I'm using sound like gibberish, it just means that's something you might want to go and spend some time studying.
Chapter 8 in you guys' textbook.
Yep. Perfect. So we have a -1 on carbon. Is that right? 1, 2, 3, 4, 5 electrons around that. And the oxygen? +1. That has to equal a 0 charge because on that carbon monoxide, we would have to tell you if it had an overall negative or positive charge. The fact that there is nothing written for a charge means that those charges on the Lewis structure have to add up to 0. So if you're not really comfortable with writing out formal charge, Lewis structures, oxidation numbers, those kinds of things, and that's something to work on. I did see that we had a good number of scientists at the supplemental instruction today. I think there was about 10 from what I saw. Yesterday there was 2, 1 in person, 1 online. So that's a really good chance to dig in, to ask them these questions that come up as you go through. I didn't have any office hours on Tuesday, but I'm hoping that I see you all going forward. We have office hours Fridays next time, 12:30 to 2. And like I said, if those office hours don't work and you're listening to some of the stuff, you're like, I feel like I'm either really far behind or I don't understand how you're getting to those answers or how the class is, that's exactly the time. Just come and talk. It's informal. We work in groups. We make sure you move forward in a comfortable pace. All right, let's go ahead and do our, well, I should see what the results were from that one. 27-2, saying it was polar. All right, I agree. H2O. Do we need to do this one? We did this last class, right?
Yeah.
Is water polar? Yes. Water is polar. We can draw the Lewis structure, and we can see the center of the positive is not where the center of the negative is. That's kind of how the thing described it before. What about CO3 2 minus? I would hope that you would need to draw out something in order to answer this question. There are a lot of steps to answer this. We've got 14 responses. If you're kind of stuck, check with the person next to you, see if you can get some ideas. And compare Lewis structures, because I see a lot of differences in Lewis structures. Good. All right, a couple more seconds to enter your answer. Decide whether this is polar or non-polar. All right, I'm going to go ahead and close this out. We haven't got a response. 29 people, one's missing. And I should probably say, for the sake of saying it, even though it's written in a number of places, iClickers would be used in class. That's why I had the geolocation turned on. If you're not in class, don't try to get into the iClickers. It defeats the whole purpose. It's like to engage you in class. It also helps me keep track of, like, if people are not here, it allows me to look and check on people. If you weren't here, then I can see through this. So there's a number of reasons for doing that. All right. To do this, I'm going to go off of, Jesse said that carbon and oxygen have a difference in electronegativity. And those are the only bonds that we have in this molecule. Carbon bonded to oxygen. So CO is polar, so I'm going to call this molecule polar. Are we good?
No, that's not the reason why you call it polar.
Okay, so the first step we have to do is what Taylor first said. If it's only one type of molecule or only atoms that have similar electronegativity, then we don't have to do anything else. We just say it's nonpolar. That's really easy. But if there are polar bonds, we have to think about the molecular shape before we can decide whether that polarity ends up canceling out or not. So how many valence electrons do we have for this structure?
24.
So how do we come up with 24, Lauren?
Well, carbon has 4, oxygen has 6, times 3 is 18, and then you add 2 since it has a negative 2 charge.
Great. Do everyone remember to add the 2 electrons because of the negative charge?
Nope.
Okay. So just a good reminder. So we have 24 total electrons to use. Then we're going to put the least electronegative atom in the middle. We can draw this out. We don't know exactly what's going to come around that. Carbon has to have 4 bonds, so I'm just going to go ahead and I'm going to draw a double bond to one of those to start with. So every single molecule in this class, with a very, very rare exception, is going to have 4 bonds. So we've used up 8 electrons so far, so that we have 18 left. So how many lone pairs do we have? 9, right? 1, 2, 3, 4, 5, 6, 7, 8. We have 16 electrons? My bad, we had 16 electrons. Right? We used 8 in bonding, 16 in lone pairs, and that's our Lewis structure. If we think about dipoles now, where are, I'm going to go in and draw partial negative on each of the oxygens, because in a carbon-oxygen bond, oxygen is more electronegative, pole is more of the electron density towards itself. So each one of those, I'm going to draw a partial negative. For each one of those bonds, a carbon is partially positive. So if we use the technique we did last class, and we say, where is the center of all of the partial positives, where is that going to be?
Center. Carbon.
It's going to be on the carbon itself, because that's the only place there's partial positive. It occurred 3 times, but it's all there. From my drawing here, where's the center of the partial negative?
There's not. Oh,
So if we say, where is the center of all 3 of those, the way I have it drawn here?
right above the carbon.
So the center of the partial negative is somewhere in this region there. Somewhere above the carbon. So based off of that, the 2 are not on top of each other, so this is a polar molecule. Why is that wrong, once again? Sam?
The actual shape be planar so that it's not square like that.
So if we draw it just like this, for the sake of getting everything on paper, we've forgotten about the molecular shape. So we only have 3 domains around that central carbon, so the shape of that molecule is actually like this. And then we put the lone pairs around it. And if we draw it with the right molecular shape, we think about it with the right molecular shape, then the center of the positive and the negative are directly in the exact same spot. So that makes this nonpolar. So if you don't have any polar bonds, you don't need to do any of this stuff we just did. If you do have polar bonds, you have to go through all these steps, and you cannot forget about the shape of the molecule. So all that Gen Chem 1 stuff is really relevant. So that is going to bring me, well, let's do one more molecule, and then I'll go back to chapter 8 that Josh mentioned.
Really?
Yes?
Double bond doesn't affect anything.
No, so actually one of the really nice things about activity 23, if you go through the entire thing, one of the parts that it focuses on for a little bit is the dipole moment, the strength of that polarity of the bond, is related to the distance between the atoms and the difference in electronegativity between them. And it has you go through and compare a few things and basically say which is more important. And one of the things that falls out of that is that it's more important how big the difference in electronegativity is. And the fact that the double bond is a little bit shorter or longer, shorter in this case, is not as big of a deal. But with that said, is the double bond in this case longer than the single bonds in that molecule? So if we have this molecule with our negative charges, which is the longest bond or shortest bond in this molecule? Does everyone agree it's a double bond?
So the
Why is that wrong?
The negative charges pull them closer together?
Hold up. We're not going there yet. Why is that wrong? Why is the double bond in this molecule not the shortest? They're all the oxygen, but it's something really special about this molecule.
Is it the valence electrons?
It has to do with the distribution of the valence electrons. Is this what it actually looks like?
The double bonds actually shared between all 3.
What's that called? Do you remember? Anyone?
Yeah.
There are 3 resonance structures. This is one of the 3 representations, and it is an average of all 3 of those. So each one of those double bonds, single bonds, is actually an average of 2 single and a double bond. So once again, another thing to go back to Gen Chem 1, look up resonance, when that happens, and what that looks like. And that's something I'm happy to go into in office hours. All right, let's go and do our last structure here, and then I'm going to show where we can get to this through our homework. Ooh, we had a bit of a split there. Sorry, as I'm jumping back and forth.
Wait, was it polar or no?
All right, so CO3, 2 minus, even though it had polar bonds, ended up being nonpolar. So the last molecule is this guy. So I'm going to give you 1 minute total to answer this question. That clock's on the screen, it's counting up. You can just discuss this right away with your neighbor if you'd like. Yeah. Wherever you'd like.
The chloride and carbon family polar bond. Yeah, that's the only polar bond. So it's polar.
Couple more seconds. Closing out. Close. Submit. Answer. 25. All right. Do we think we're in agreement on this one?
Total agreement.
Everybody in this class that did respond said that this is polar. Why would we say that this is polar? New voice, please. Why would we say that this molecule unanimously is polar?
Because of the chloride.
So we're going to be careful with terminology. Ide means negatively charged, so it's not a chloride. What is it? Chlorine. So it's a chlorine atom. And so because of the chlorine, what about the chlorine?
All the other bonds are non-polar, but that one bond, the chlorine and the carbon, would be a polar. So for it to be completely non-polar, they would all have to be non-polar.
Great. So in this molecule, and remember, we always, when we're talking about polarity, we're talking about bonds. What's bonded to what? So the fact that there's a carbon bonded to a chlorine. If we look at our electronegativity table, what are the values of those? That was in the front of activity 22 that I handed out last class. Does anyone have that with them? What's the electronegativity value of carbon? What's the of chlorine?
Chlorine is 2.87.
2.54, 2.87. Is that a polar bond? What's the cutoff of difference in order for that to be a polar bond? About 0.4. Is that greater than 0.4 or less than 0.4? Less than 0.4. So while they are different atoms, that is not a polar bond. On an exam, I will give you a table similar to that has electronegativity values, so you have to go look to see is that a polar bond or not. You have to use the data of electronegativity values to support that. So that is not a polar bond. What about carbon and hydrogen? Those are not the same atoms. Isn't that polar? What's the difference in electronegativity between those two?
24 or 0.24.
0.24, also nonpolar. So this molecule is nonpolar because there is not a single polar bond in it. And let's see how everyone responded. Ooh. Yeah, so sometimes it's great being in alignment with everyone else. Sometimes it's not. Okay, so one of the things I wanted to show really briefly is when you are in your homework, and I think I have to click there. So if you, I think this is today's primer or Monday's primer, I can't remember which. If you're working through these and you get something wrong, it's set up, like I said, to kind of give you an idea of where to study. So in this particular example, I'm good on the first two ideas here, concepts. I don't need to work on them, but if I do, I could click on them and I could go to the ebook right here. I could click on that and it's going to pop open a direct access to the ebook. So that's one of the really nice things about having everything integrated together. Not only does it take you to the book, it takes you to the section of the book on that topic. If I go back, and that's more important on the ones that you get wrong. There's also tutorials and additional help buried within those. So all three of those are really good resources if you get something wrong. The other component of it is if you're in your homework, it's going to look more like this. And let's say, I know this is Gen Chem 1 stuff, but I'm not 100% on it. So how do I go review this? So if we go to references, we can go to periodic table, organic chemistry table, significant figures. But under review topic, that's where it has a link to that section of the book, which is Gen Chem 1, but it's still directly accessible for you in the materials that you have. So those are just some of the resources, some of the ways to map back to resources you have within the book that you've paid for. There's tons of other resources out there, but this is just, I want to make sure everyone was able to navigate that component. All right, so by the end of today's class, I want everyone to be able to identify polar bonds. Can we do that? Getting closer to that? We're going to start diagramming the interaction between molecules. A lot of this feels like memorization and like these steps you have to go through. But if you can't get in the Magic School Bus, does anyone see the Magic School Bus? Am I too old to be referencing that? Does it still exist?
Yes.
Okay, if you have not seen it, Miss Frizzle drives a school bus that gets really big or really small and goes places that you shouldn't be able to go. And you see things at a really crazy scale. So Miss Frizzle goes to organs inside the body, or she goes to the size where it's actually atoms and molecules. And so I'm going to have us go down to the level where we're starting to look around as if we were able to see molecules around us, and thinking about what do those interactions look like because of the polarity that we just discussed. So I want you to be able to diagram that. I want you to be able to draw it out, and that's something we're going to be doing today. In order to do that, we need to compare and contrast different types of intermolecular forces between two different molecules, and also thinking about what are the strengths of interactions inside of a molecule and how do those relate to each other. And then we're going to be talking about what are some of the strongest intermolecular forces you can have in a particular molecule based off of what it's composed of. And then we're going to think, how does that relate to boiling point of a pure substance? This is one part of the semester where people get confused between this week and next week. So I wanted to make a distinction. This week we're talking about if you have a pure sample of water or of ethanol or of benzene or whatever it is. You only have one type of molecule, and that molecule is in a sample with a lot of other ones. Billions and billions and billions of those molecules. So if you were in the Magic School Bus, you go in, you look around, you're only going to see one type of molecule bumping into the other ones. If it's a liquid, you're going to be in the liquid. If it's a gas, it's going to be surrounding you. If it's a solid, you're going to be looking at it probably from the outside. Next week, we're going to be talking, can I steal this for a sec? More about these types of samples. So where you do have, the majority is usually water in the case of solutions that we're looking at. And within that solution, you have a lot of little things that are floating around. And we can describe those little things floating around as a percentage of the total molecules. We look around and be like, well, there's 1 out of every million water molecules. There's a sugar molecule. 1 part per million. Or we can talk about a molarity. We can talk about a number of different ways. So don't get confused about, next week we're talking about why does sugar dissolve in water and how does it change water's properties when it does dissolve. Compared to this week, we're talking about how does water as a pure substance act, how does ethanol as a pure substance act. Okay? So we're going to be focusing this week, how does a pure sample, how the molecules interact with each other, which depends on the polarity of the molecule and its weight. Next week, colligative properties, that's where we're talking about the interaction between a lot of something, the solvent, and the solute. And then if it does interact to the point where it's dissolved, then how does that change the properties of the solvent? All right? So let's see if we're all on the same page from last class. Answer this question on your own, please. This is question number 1 on the worksheet, maybe? Today's worksheets are the one that is a single page front and back that I handed out today. If you don't have one, let me know and I can grab one for you. Anyone else need one? Has the boxes on it. Alright, a couple more seconds. Looking at a water molecule, have one drawn here. Alright, 26 responses. Feeling good? Feel like we're all on the same page? Closing out. Alright. Not all on the same page. Split kind of all over the place. So, new voice who has not spoken, answered any part of any question today. Who wants to share your thoughts and why you might disagree with some of the answers up there? Okay.
Right, but my thoughts are oxygen's charge is usually -2, and hydrogen's charge is usually +1. There's 2 hydrogens, so they cancel each other out, become neutral.
So one of the things I really like is that you're thinking about trends on the periodic table. It's fantastic. In this molecule, do we have positive and negatively charged species? And how do we know that? So it's not about necessarily liquid. What types of molecules do we have charges in? Ionic. Only in ionic compounds. And in this one, we can see that it's not an ionic compound because we have straight lines drawn between 2 different atoms, and those lines mean that the electrons are shared. The question is, if the electronegativity difference is really, really, really big, then we'll have ionic compounds. And if you were to find oxygen in an ionic compound, it will be a 2- charge, because it's a group 6 and it needs 2 electrons to get to the isoelectronic state of the nearest noble gas. So in this case, the electrons are shared. What's missing from this is the 2 lone pairs. And so if we had a full negative charge on the oxygen, that's saying that the electronegativity difference between that and this connection is so big that it actually steals the electrons from the thing next to it. So then why is it a partial negative charge? Why can we justify that it's a partial negative charge? How do we think about that? So instead of stealing the electrons, we can draw it kind of as a dot structure, right? With those electrons between. That if we say that they're right in between the 2, they're going to be neutral. But are those electrons really sitting right in between the 2 atoms? Oh. Okay, so there's a molecular shape that's different, it's bent. But in addition to that, one has a stronger pull on the electrons than the other. Which one has a stronger pull on the electrons? Oxygen. And so those electrons, if I can redraw that, are going to be found a little bit closer to oxygen more of the time, which means that hydrogen feels a bit deficient of its electrons, and oxygen is more rich in its electrons. So we're going to go ahead and say that there's a partial negative and a partial positive charge in that bond because the electrons aren't shared equally. And then we also want to think about the shape. And so that's what gives it an overall polar molecule. So let's think about water. If we have water that's evaporating, answer this question on your own first. Pick an option, and then once you've picked an option, converse at your table, and then you can change your answer if you want after you've talked to your table. And if you haven't noticed, on your phone, if you wanted to zoom in, you can pinch and zoom in on iClicker of the screen capture if you ever weren't close enough to one of these big screens. Does anyone disagree? So maybe that's a group trying to find the phase change. Disagree?
Yeah, we're going to be
All right. I'd like a new voice to discuss what your group said and why. Aislinn?
We said, or I said that it's a phase change and not a physical change, not a chemical change. So technically the bonds wouldn't break because that's a chemical property of it.
Love it. So thinking about chemical versus physical changes, thinking about a chemical change is defined by the breaking of covalent bonds. And if we're breaking a covalent bond, we're changing it to a different chemical. Is water still water after it evaporates? Can we get it back the exact same way by doing something non-chemical? Cool it down, and it condenses again. Okay. If you ask the general public this question, 75 to 90% of the time, people say true. Or if you ask them to draw it, then they draw those atoms being disconnected from each other. One of the terms that we're not going to use in this class, that I heard a couple different places, is the bonds between the molecules. They are interactions. If you have two water molecules, they are not bonded together. Those two water molecules are attracted to each other, and that's kind of the purpose of today's class, is to think about those interactions. Is anyone thirsty? Want a cup of water? So we've got these water molecules, and in this case, they have magnets to kind of simulate the interactions between the water molecules. So I'll kind of pass these around and keep it as a group. I'll pass one in each direction. I want you thinking about the difference between bonds or intramolecular interactions and the attraction between molecules or intermolecular. So the next activity I want us to do is I want us thinking about that magic school bus. We're zoomed in, we're looking now at water molecules, and we have 5 temperatures. We have these little glass boxes of water. And I filled the first one in for you. So the first box with water has molecules at negative 265 degrees Celsius. So you notice gravity, you notice how many molecules there are, and each water molecule is just represented as a sphere. We're not getting too complicated showing the shape and all that stuff right now. But the shape is important for how it will look at different temperatures. So I want you as a group to think about how am I going to represent those water molecules at negative 75 degrees centigrade, 5 degrees, 85, 125, and then if I had a 6th box, even warmer than 125. What are they going to look like? What's similar between the boxes? What's different? So go ahead and do that. Write those out. Draw at least 10 spheres in each of the boxes. And think about it as a closed system where those water molecules aren't going to escape that box, but think about how they're going to look. Sorry, we're doing this for water. It looks like I extracted one of them in the text, but not the other. Please do this for water.
So the higher the temperature gets, the farther apart. So they're still technically together at -75 and 5 degrees Celsius. And that. But they get further. Yeah, that's what I was thinking. Oh, we're the same thing. Okay. Would there be a difference between the way ethanol would use it? Because that says ethanol. Or ours says ethanol. Those are all what ethanol.
I'm just drawing
Does everyone have something drawn now?
We're still thinking.
So it's still good.
I was wondering, what is in the transition?
What would be the difference? This group here mentioned phase diagrams. That's something from like your thought process. So you remember phase diagrams? So think about phase diagrams. If you don't remember the word, you can pull that up. Think about what that means for this. It might contradict some together. If you're sitting there looking at it, so it might not be something you can draw on Saturday. Think about it. Okay. I want the underpinning of this discussion to be based on what we just talked about, which was phase changes, and just before that, polarity. Okay? So polarity should be part of your conversation, your discussion about what these boxes look like and why. So if we draw our second box here, how do we describe the first box? What's the best way to describe that? Solid. Frozen. Is there, do you agree with the statement? There is no movement of those molecules of water because it is frozen. Amber disagrees. What do you say?
They're vibrating.
They're vibrating. Okay? So there is energy. Is there ever a temperature at which we have zero energy and those molecules are not moving at all?
0 Kelvin.
Absolute zero. That is the definition of absolute zero, is where all movement stops. So negative 273.15 Celsius is absolute zero, or 0 Kelvin. So we do have some movement. So if we were to zoom in and look at that and give it a little bit of time, we'd see a little bit of buzzing, a little bit of vibration in those molecules. Then we're going to warm it up to negative 75 and have that box next to it. I saw a lot of people draw expansion, that those molecules are now further apart from each other. Does that sound reasonable? Would anyone like to agree with that and say why, or disagree with that and say why not? We're going to share other voices. I appreciate the enthusiasm. Danielle?
It'd still be really frozen, but it'd be vibrating like a little bit harder because there'd be more energy because it's warmer than it is.
So we have a very common misconception that solids expand when warmed up. Think about a block of ice. If a block of ice is in your freezer versus if it's sitting on the counter right before it melts, does it expand a lot? It doesn't expand at all. And if we were to cool it down, granted we're talking about minus 20 degrees Celsius to minus 1 degree Celsius. But if we went all the way down to negative 75 degrees Celsius or 265 degrees Celsius, there would be no, or very, very, very little measurable change in the volume or how much space those molecules take up. So how would I draw this to be accurate? What would it look like?
The same.
Pretty much the same. The image would be, let me do it a little bit bigger. Okay, so pretty much identical. The other thing that we see sometimes is that people think that when it's warmer, it defies gravity. And so it starts floating up. So one of the things I was trying to show with this first image is that this is a glass box, that its gravity is pulling that solid down to the bottom, and they are compact. They are in a very ordered fashion, right? There's a uniform way that the molecule is arranged with each other. As you can kind of see with these ones, see how they start to form these really nice structures that have repeating units to them? So that's what most solids are going to do as well. So then, this group over here, with Taylor, I believe, mentioned a term that was very useful in thinking about what happens here. So what was the term you described?
Phase change.
So phase change, and you talked about phase diagrams and how that might play a role. So then how did your group use that to discuss what might happen between negative 75 and 5 degrees Celsius?
Well, we said that during if you know what a phase diagram looks like, you know that during the phase change, it transitions. I'm sorry, I'm losing my train of thought. But you know that say water, for instance, when it's frozen, it doesn't change its phase until it completes, till it reaches its melting point, and then there it will change and the molecule will go apart.
So the phase diagram speaks about energy required to get to a phase change. Temperature is the way we usually talk about that. Once you get to a certain amount of energy or a certain temperature, then those vibrations that started out really small got more intense, and then they get to a point where now they've overcome a barrier. So if we're thinking about those interactions between the molecules, why do those molecules stay put next to each other, and why are they not any longer in the liquid? What's keeping those molecules together or moving apart? So Jesse mentioned the term hydrogen bonding. What is that? How does that relate?
It's the possibility of the hydrogens bonding to the oxygens.
So we're going to be really careful with our terminology and the term bonding, because a lot of times that means a covalent sharing of electrons in order to fulfill an octet. So what's another term you could use? So there's an interaction between the partially positive hydrogen of one and the partially negatively charged oxygen on the other molecule. So think about it as magnets, right? That's why I was handing these molecules around. And do you mind passing it to the next table? I don't know if they've gotten a chance to see it. And so think about it like magnets. They're weak magnets because it's not the same as forming a covalent bond, but there's attraction between those molecules. And because of that attraction, if you don't have a lot of movement, then that's going to be enough to hold those things together. Once you get enough vibration, now they're no longer going to be enough energy to hold them together, so they're going to start to move past each other. They're still going to be attracted to each other, but now they're going to be moving, and when they move, you're going to have them taking up whatever space the container is in, as opposed to solid that keeps its original shape when it was frozen. And what else would I use to describe what's happening with those molecules? If we sat there and looked for a little while at 5 degrees Celsius, that was not happening at negative 75. What's different about the box at 5 degrees Celsius?
It's filling up the space, not so much keeping its shape.
Great. So it's about the shape of the molecules, what container they're taking up, but what else?
They're colliding
So now they're colliding, and they're, I would even say, sliding past each other. So now there's movement. There's not just movement of vibration, there's movement of what we call translocation. It's changing its location. It's moving from one place to the other. Okay? So with that, why don't you take another 2 minutes? Think about the last two boxes. What should those look like? And how does the interaction, the attraction between the molecules impact how those last two boxes look? Asking everyone to get a chance to look at them. Set up there so you can just keep them or pass them to everyone.
Well, none of it's going to go from the liquid to the gas.
So if I open this and left it here, it would never evaporate. Is what you're saying?
Well, it's not going to. Well, I guess there's that. What do they call that? I forgot.
Vapor pressure.
Vapor pressure. Yeah.
Think about why. So what's the attractive force between
I'm just thinking
molecules?
about how y'all are saying with
Yeah.
phase diagrams.
That's how you can force it to go over one. And if everything has enough energy to be at over the boiling point, then everything will evaporate. And think about what it means when it's at room temperature, 25 degrees Celsius. What's going to happen if you open that up? Why does that happen? Okay, so can I have someone help describe a new voice for what we're going to see at 86 degrees Celsius? What's going to be the same? What's going to be different than 5 degrees Celsius? Sarah?
So coming from 5 degrees is on the bottom, but since it's getting warmer, some of the molecules are going to start going up.
What do you mean going up? So are they going to be...
Like evaporating almost,
Not right.
or starting to evaporate.
So does that agree with the phase diagram that you were talking about earlier?
No.
So the phase diagram says that you have a phase transition at the temperature at which things boil. So we're not at 100 degrees Celsius yet, right? 0 degrees is freezing of water, 100 is boiling. That's why we love Celsius and we hate Fahrenheit. Yes, Mackenzie?
It's just more sliding.
So what would look similar and what's different? So you said more sliding is a different.
Yeah, but it's not a difference really. Maybe just a little more spread out, but it's still like, yeah, it's still at the bottom. It hasn't like rose like yet.
Okay, so there's more sliding past each other, or I would argue to say it's faster. So there's one part of this diagram that I have left out. What did I add and why? Tracy, what's added and any idea why?
Molecules are free.
There. So we said that above, in the box above the sample, the atmosphere, the space above it, that there are some molecules at 5 degrees Celsius, and there are more at 86 degrees. So that goes against what I just talked about with this group's discussion with the phase diagram, that you have to be at the boiling point in order for something to change phases. Yeah?
Would this be kind of like humidity?
Yes.
Okay.
Exactly. So we know that a puddle that forms after rain, we don't need to boil in order to get it to evaporate. So what's happening? Why can water evaporate below the boiling point? What happens when you boil something? Let's do the last diagram and then we'll talk about this more. So what does 125 look like? Spread out. takes up the entire container's
Would it be completely
space.
evaporated?
Are we, so we are above the boiling point, the entire sample is above the boiling point, so everything exists as a gas. If you have any left, it's because it hasn't gotten to the right temperature yet. What else? Whew, that's not what I wanted. What else can I use to describe what those molecules look like? Doing a great job here. If we stood there and looked at them for a little while, are they static there? Or is there any movement? What's the interaction between those gas molecules look like? Is there a lot? Is there a little? Is there an attraction between the gas molecules? When we talked before about as a solid, you have that partial positive and partial negative from one water molecule to another, and that's why they form a solid. And once we get enough energy, they start sliding past each other. Once they're in a gas, how much attraction is there between these two molecules? None. The ideal gas law says there is zero interaction between them. Reality is slightly different, but for our purposes in this class, we can say there's none. Until you cool them down and they happen to be moving really slowly past each other, and then they start getting attracted to each other again. So let's think about our sample at 5 degrees Celsius. Is there movement? There's movement. All the molecules are moving past each other. Are they all going exactly the same speed? The molecules at 5 degrees are moving slower on average than the molecules at 86 degrees Celsius. But it's on average. So those molecules are moving at a big variety of different speeds. And if one happens to be moving at one point in time faster than all the others through the middle, and it gets to the surface, the question is going to be asked as it moves past its neighbor, am I going fast enough to overcome that intermolecular force? And if I'm not, I'm going to stay in the liquid, which is most of them. But every once in a while, one of the molecules is going to be moving really fast as some of the others are moving really slow, even just for a brief amount of time, and then it's going to go past and it's going to float out into a gas. Does that happen at 86 degrees? Yes. The same amount as at 5 degrees? It's going to be happening more often because these molecules are moving past each other on average faster, which means there's more of them moving fast enough when they get to the surface to overcome that intermolecular force, that attraction, and go out to become a gas molecule. These ones are going to bounce around, and if they come back and hit the surface, they're going to become part of the liquid again. But then there's going to be another one that goes into the gas. So you're going to have equilibrium between liquid and gas that's going to give you humidity or vapor pressure. So your homework this weekend is going to have some components that talk about vapor pressure. Vapor pressure says how much pressure is generated from these gas molecules. The more molecules there are, the more pressure you have. How does the interaction between these molecules, the strength of the interaction between these molecules, change the vapor pressure? So if we compared water to a nonpolar compound that weighed about the same, what would have a higher amount of molecules in the space above it? The one with stronger or weaker interactions between them?
Weaker.
Why weaker, Tracy?
They can break free easier.
Because with the same amount of speed, they can go past, and it's not going to be as strong of an interaction, so they're going to have an easier time, and more of them are going to be found in the gas phase. It's going to have a higher vapor pressure. So you can look at a table of vapor pressure and say, this has a really high vapor pressure at the same temperature, so I know those have really weak intermolecular forces. So that's part of kind of tying things together. I really want us thinking about what this looks like from the individual interaction between molecules and why that results in a physical interaction we see. So that is part of chapter 11. That is, you have a number of problems in homework that relate to that. And we're going to spend a little bit of time discussing some of those things here. So it's a bit curved, so you'll see if you, in the homework, you'll probably link out to one of the chapters for it. But as temperature goes up, the vapor pressure kind of goes up. And then there's actually a way to look at that and figure out boiling point from that when you have, there's a lot of cool stuff you can pull from that. So go ahead and take a look at those images when you get a chance to look in the book. So go ahead and pull out packet 27, which is the one I handed out today. The first page is kind of what we've already talked about. Please do go ahead and read through that. Anyone see the packet? The second question is a clicker question that's up right now as well. When you get there. Once you finish that first page, go ahead and flip the page. Start working on the critical thinking questions. There is a lot of information to take in those graphs, but the questions guide you through the information in those tables. Yeah, go ahead and answer those two. Yeah. So go back and go back in. Open. Why does it say? Join again. I don't know why it was just not responding. If you haven't already, submit your answer to question 2 on the first page. Got another 100% answer? Why is this liquid has a stronger average intermolecular force? Even though it's the same compound, why is the liquid form stronger? Sydney? Oh, sorry, there's 2. I was looking at this Sydney for now. Okay, go ahead.
Well, you just stated that the higher the vapor pressure, the weaker forces of the interactions.
True,
That was my thought process.
but that's if you have two.
Gases
So what you're talking about, Sydney, is if you have 2 different molecules that have different intermolecular forces. This is saying water is liquid or water in the gas phase. So Sydney, can you say what you said?
You said for gases or diamonds.
We said there's no intermolecular forces between gases. Because once they're in the gas phase, they have to be close to each other to feel that attraction between a partial positive and a partial negative. Okay? So go ahead and start working through model 2. If you're just looking at the table, it's a lot of information. So flip to the next page and start going through the questions. It'll guide you through the information in the tables. So start working on critical thinking question, I think it's 3, and kind of go down from there. And our team is going to try to jump between tables to make sure that you're on the right track.
Yes, just the polar. Only, okay, they probably have stronger.
Which name is this? And then
Or there's things already out of one. Yes. Yeah. I'd say they can, because you have to put it at a higher temperature to get to the boiling point.
So think about that, and that's Might be a good time to check. Looks like not everyone's as confident. That's gonna be important. For you, explain how you determine whether or not
Well, carbon and hydrogen said earlier that they're basically not polar. Difference between the two is that they're polar. Yeah. And there's no oxygen molecules on the alkane compounds. So that's why some of them are all not polar, because they're not using negative of both the ketone and alcohol. So they're all have oxygen molecules.
So I just wanted to wrap up a couple things with the beginning of this packet. Once again, this packet has some really rich material in it. If we're looking at the term alkane, what does that mean?
No double bonds.
Okay, true, but what specific, so if we're looking at the table that has all alkanes, what stands out? All carbon-carbon and carbon-hydrogen bond. That's it, that's called an alkane. What about a ketone? What makes something a ketone? There's an oxygen, double bond, and a carbon, and even more specifically, that carbon has one carbon on either side. So that's called a ketone. And an alcohol has an oxygen as well, but in that case it has a carbon on one side and a hydrogen on the other. And something really special about that carbon is it does not have a double bond to oxygen on it. If that carbon has a double bond to oxygen, that is no longer an alcohol. That's something totally different, called carboxylic acid. Okay, so polarity. We're looking at, once again, we're going back to what we talked about at the beginning of class. Are there any bonds that have atoms with different electronegativity in them that are sharing that bond? And so hopefully we see that alkanes, you can see across the board, there's no polar bonds, so we're not worried about it. Nonpolar. Ketones have one polar bond. Alcohols have two polar bonds. So then the next question kind of gets at, well, what happens to the boiling point as the molecular weight goes up? Did anyone figure out the trend? That as the molecules, each individual one, we're in the metro school bus, right? We're looking at these molecules and we're in a sample of only one of them, if those molecules are all moving around, which one is going to boil with less energy or at a lower temperature? What trends do we see with weight? Jason?
The lower the weight, the lower the quantity.
Why? Why is it the lower the weight is that the less temperature you need to get it to in order for those molecules to become a gas?
Because there's less to boil, there's less molecules to like.
Same number of molecules, we're not going to be talking about a different number. Sarah?
There's less, intermolecular forces.
Same types of intermolecular forces. You know?
Is the intermolecular force weaker?
So there is maybe a slightly weaker intermolecular force because the London dispersion forces or the induced dipole, there's fewer of them. But that's not really the main reason that as something gets heavier, the boiling point goes up. Taylor?
That's right, but I said, so as the molecular weight got heavier, it takes more energy to overcome those forces, and that's why the boiling point is increasing.
So if you have two molecules that are different weight, but the same energy, are they going to be going the same speed? If you have a boulder and you have a marble, and you push them with the same amount of energy, are they going to be going the same speed? So the one that's heavier requires more energy to get up to a high enough speed to overcome those attractions between the molecules. So not only do we have to think about now how strong is the attraction between them, but how much energy does it take to get them to speed to then be able to overcome the molecular forces.
So it's not more molecules, it's just the molecules weigh more?
The molecular weight says each molecule weighs more because there's more carbons in it, there's more hydrogens or whatever it is. And so being heavier, instead of just the water molecules going past each other, imagine if this one weighed twice as much, you give the same energy, instead of going this fast, it's going to be going this fast in a solution. So when it gets to the surface, it's going to have a much harder time becoming gas. So the rest of this helps kind of outline patterns of thinking about intermolecular forces and how boiling point and molar mass relate. So the last thing I want to put up here for today is that we have a terminology for what these different things are called. Let's do one clicker question. Now we're at the end of class time. So let's just have this question up here, and then as soon as we have an answer to this, I'll put up the learning objectives so you can reflect on whether you think you're able to do the things that I wanted you to be able to do. So these are the different names for the interactions. We have an ion inducing a dipole. We have dispersion, London dispersion forces, or induced dipole is B. We have hydrogen bonding, we have dipole-dipole interactions, and we have ion-dipole. Which one of these do you think is the strongest intermolecular force? Couple more seconds. Anyone got an answer in? So I want you thinking about this answer. I want you to go home with your homework. Why is it that the ion interaction with the dipole is the strongest interaction out of all these, even more so than what we're told in biology? The strongest interaction in intermolecular force is hydrogen bonding. So I'll post these slides. There's a little flowchart I have to decide what kind of intermolecular force it is. And I will leave up our learning objectives. If you look at this list and you're like, I don't know that I can do all this, then think about that and what it means for your study coming up.